Some problems resist direct programming. We add one case, then another branch, then another rule, and the program grows faster than our understanding. Part of that difficulty belongs to the problem itself, but part of it may come from the language in which we are trying to express the solution. The book structure and interpretation of computer programs gives us a more powerful move. Instead of only writing a larger program, discover the problem's vocabulary. Decide how its pieces combine. Build expressions from those pieces and define what the expressions mean. We pay once to design the language, then solve a family of problems in the language of the domain. We will learn the move inside ordinary Python. A report becomes an inspectable tree. That tree gains an evaluator, a type system, multiple interpreters, and rewrite rules. Then the same ideas return to symbolic integration, where search proposes an answer and differentiation checks it. Python, JSON, Scheme, and Unix are examples. The subject is the meta move. Build the language, then solve the problem. Start where the need is small and unmistakable. Here is a perfectly ordinary request. We have a small table of purchases. Keep the completed ones since January, add up how much each customer spent, and show the top 3. In Python, that is one short loop. It filters the rows, collects the totals, and ranks them. For this one question, that is exactly enough.
And short loops are allowed to stay short, right?
Exactly. This episode is not about declaring war on ordinary code. It is about noticing the moment when an ordinary program wants to become something else. The loop asks 2 questions of every transaction. Was it completed? Did it happen after the cutoff? If both answers are yes, add its amount to that customer's running total. Then sort those totals and keep 3. Rows that fail a test simply fall away. The survivors collect into customer buckets, and the result is a clean little ranking. B spent 520, Chen spent 515, D spent 500. The program is readable, direct, and correct.
So where's the problem?
There is no problem yet. A fixed question deserves a fixed answer. That is where this story starts. The trouble begins only when the questions start moving. The fixed report starts acquiring knobs. Group by region instead of customer. Add a grouping parameter. Average purchase instead of total revenue. Add an aggregate. Each local change is reasonable.
Then finance asks to save a report and run it every Monday. And I want to inspect the report before it touches any data.
A function can certainly create a report description. But now the description itself wants to be the thing we work with. It needs its own vocabulary, structure, and plan for execution. In other words, the program is ready to become a language. So stop staring at the loop and name the moves it contains. A source. A condition. A field comparison. Group by. Sum. Sort. Take. These are not implementation details anymore. They are the verbs of a small query language. We can compose them as ordinary Python functions, one result flowing into the next. The nesting is a little backward to read, but it exposes the algebra. Each operation takes a report-shaped thing and returns another report-shaped thing.
So the important rule is that a combination is still a report.
Yes, that is closure under composition. It is the reason a small vocabulary can build large programs. We have not invented new punctuation. We have found the kind of thing our operations should preserve. Now give the same vocabulary a friendlier Python surface. Start with the transaction source, add a condition, group it, sum it, sort it, take 3. But watch carefully, none of these calls reads a transaction. Each call wraps the previous description in one more operation. The finished query is not a result. It is a tree made only of lists, names, strings, and numbers. That means it can be printed as JSON, stored in a file, sent to another machine, checked for mistakes, or changed before any data moves.
If I replace customer with region inside the tree, I have changed the report without changing the engine.
Exactly, the program is now data. A technical name for this tree is an abstract syntax tree, but the important name is simpler. It is a description of work. We can finally say what we built. Primitives, sources, fields, and literal values. Combination, one operation wrapped around another. Abstraction, a named report that can be reused. And interpretation, the evaluator that will eventually run the tree. Unix pipelines and SQL make related choices with different syntax. The syntax is not the main event, the algebra is. The original loop was still the right answer for one immediate question. The language earns its cost when descriptions must be changed, inspected, saved, or shared. We did not begin by writing a parser. We changed what the program is made of. Next, we follow the consequences. Once a program is data, what else can we do with it before it runs?